Okay, so welcome to Statistics Seminars. I'm very happy to introduce Dr. Mark Risser, who is currently a Cascade Research Scientist at the Lawrence Berkeley National Lab in Berkeley, California. He received his PhD in statistics from the Ohio State University in 2015. Dr. Risser's primary research is in spatial environmental statistics and Bayesian modeling. He also has interest in spatial temporal statistics, computational methods, stochastic differential equations, data visualization, teaching statistics, hybrid education methods, and meta-analysis. So today he's gonna share his recent research on Bayesian inference for high-dimensional non-stationary Gaussian processes. Let's welcome our speaker, Dr. Risser. So please take it away.
Thank you so much for the introduction. It's a pleasure to be with you all today here over Zoom. So yes, my name is Mark Risser. I'm a statistician who's working at the Lawrence Berkeley National Lab. Just to give a brief overview of the talk, I wanted to spend a few minutes here at the beginning just giving a brief introduction to Lawrence Berkeley National Lab and what it's like to work there as a statistician. So I ended up here started out as a postdoc, and now I'm in a research scientist position. In some ways, I don't know how I ended up here. I didn't know all that much about national labs before I came here. So, but there are some great opportunities for statisticians, and just wanted to give a brief overview. So we'll do that, and then we'll jump into the talk. Lawrence Berkeley National Lab is the mission statement there. You can see where our goal is to, in a very broad sense, bring science solutions to the world. So it's very much sort of an applied science, basic research type of place. We're primarily funded by the U.S. Department of Energy, although there are other funding sources as well. The sort of research areas cover the spectrum really of all kinds of different things, from physics to computer science to engineering, applied math. I'm working in a climate group, which I'll say a little bit more about in a moment here. And then there's certainly some famous alumni from Berkeley Lab, a number of Nobel laureates, and also people have discovered some periodic table elements here, which is kind of a cool thing. So we are located, if you can see my mouse, hopefully we're located in Berkeley, California, which is sort of Bay Area, right across from San Francisco, Northern California. I'll have to brag just a minute. I probably have the best work view that I will ever have in my life. So Berkeley Lab kind of sits up on the hill and looks out across the city of Berkeley. So this right here in the foreground is the UC Berkeley campus, and then kind of across the water is San Francisco, the Golden Gate Bridge. So it's really great place to work as far as the views are concerned. Like I said, I work in within the Climate and Ecosystem Sciences Division, which kind of has a number of program domains, from thinking about climate and climate change to more ecological sciences to Earth systems and society, sort of how humans and the climate interact. And our goal, again, a kind of very large scale, is to develop capabilities and knowledge around understanding and predicting of the Earth's climate system. So kind of at a very large scale. There are a number of undergraduate and graduate research opportunities. So I put up a few of those here. There's internships that can range from a handful of weeks to a handful of months. These are great opportunities, like I said, for both undergrads and grads. It does require kind of getting paired up with a DOE scientist, someone who works at Berkeley Lab. So that would be someone like me. So if this is something that you might be interested in, I'd be very happy to chat offline with anyone about these types of opportunities. There's also a very large postdoctoral fellowship program at Berkeley Lab. Again, that was my gateway to Berkeley Lab. I started there as a postdoc. This can be 2 or more years. In my specific division, these are joining projects related to climate and climate change, or actually also climate extremes. I think doing a postdoc at a national lab does really keep your options open. It's a very active research focus, so that sets you up really nicely, I think, for a tenure track faculty job. Or you can do what I've done and transition to a sort of more of a research scientist sort of permanent position in the national lab setting. So I think doing a postdoc at a national lab is a great experience. And and does really set you up for, you know, a variety of careers afterwards. Did just want to say a quick note about what it's like to be a statistician at a national lab, in that it's it's a very different research environment relative to the university. You know, my goal in my job is definitely, I'm not a consultant, so it's not about kind of doing one-off projects. It's more about kind of developing long-term collaborative research agenda. It's a really exciting opportunity, I think, to apply sort of advanced statistical techniques to cutting-edge, highly relevant research. You know, you get a chance to work with experts in the different scientific domains, so that kind of is a great way for a statistician to apply their methods to real-world problems. On the other hand, there is not a formal statistics group at Berkeley Lab, so that's a little bit different, I guess. But there are connections with the stat department down on campus at UC Berkeley, so there's a chance to kind of stay active in seminars like this one, and reading groups, and other things like that. So that's my very brief overview of the National Lab, what it's like to be a statistician at a National Lab. I think it's a great place to work, and if anyone has questions about that, I'd be happy to chat offline or email or whatever. So that's the end of my little sales pitch, and we can jump into the talk now. So the big picture idea here involves Gaussian process modeling, and I think there's probably a diverse enough audience on the call here. I just wanted to give a very basic overview of this. So by process here, what we mean is a stochastic process. So this is a statistical model for a collection of random variables indexed over some continuous domain. So for example, time or space, or could be a lot of other different things. And then the Gaussian here means that you take any finite collection of random variables from that domain, and they will have a multivariate normal distribution. So as probably most of you on the call know, this is a really popular tool in statistical modeling. It shows up all over the place, from spatial environmental stats to machine learning, emulating computer experiments, complex mathematical models. If you're not familiar with this, you can really think of it as a non-parametric or nonlinear regression. So to keep things stat 101, we all know that the goal of simple linear regression is to determine a linear relationship between here just one input, the explanatory variable, and one output. And in this very simple contrived example, a linear model captures this relationship well between your midterm and your final exam score. So that's something I think we're all very familiar with. If we take a different example, so here's a time series of daily temperature measurements from the San Francisco airport over a couple years. Clearly, a linear model does not capture this relationship very well. Kind of misses out on a lot of the important features of the time series. If instead we fit a Gaussian process to these data, that's the red line you can see there now. Again, you can see that we've much better characterized the relationship between time and temperature. You can kind of see the annual cycle here, and even sort of differences within each year. There's kind of an increased bump here in the late summer in the second year. Anyway, point is that we've now characterized a nonlinear relationship between time and temperature. And so again, you know, the Gaussian process has various statistical parameters that we need to estimate, and talk about sort of fancier framework for doing that. Things that talk about the smoothness of this line, and how you know, how much variability there is about that line, things like that. So that's a very quick overview of Gaussian process. Hopefully, give you just a bit of a picture to keep in mind as sort of a non-parametric or a non-linear way of doing regression. To be much more formal here, and to put things into a Bayesian framework, set up some notation here. We'll let Z be a realization of our stochastic process that we're interested in, or defined over some subset of Euclidean space here. The examples that I'll be sharing in the talk later are all spatial domains, so that'll be like a two-dimensional input space with latitude, longitude as the dimensions of that space. Anyway, we can define a linear mixed model here for our observed process, where we decompose what we've observed, Z, into two components. Y here is a latent process, a spatially dependent random effect. Epsilon is our error process, where these two guys are independent. and we'll suppose that our error variance is known up to some parameters theta z. The Gaussian process model comes in here down in our latent process y. So here's our notation for a Gaussian process. These two components describe the first and second moments of the Gaussian process. So x beta is some linear mean function, and cy here is called the covariance function, which describes the covariability in y for all possible locations in our domain. So this c is just the covariance of this latent process y. Turning this into an actual data model, so let's say we have some locations, some fixed locations, n of them, where we've observed this process. So this is the observed locations. The distribution, what our model here specifies is that the distribution of our data given the latent process and parameters is normal, centered on the latent process, where the covariance here is a diagonal covariance. That conditional on the latent process, the data are independent. The latent process model, again, conditional on the parameters here. This is the Gaussian process assumption that says that the distribution here is, again, normal, multivariate normal with a linear mean and a non-diagonal covariance matrix here where the elements of that guy come from the ij element comes from the pairwise covariances from our observed locations. And by the way, I'm more than happy to take questions throughout. If I'm going too fast or am missing anything obvious, please feel free to chime in. To make this a bit more, right, okay, so to make this a bit more Bayesian here, in terms of actually using this model, it's often useful to integrate over that latent process to get at a marginal distribution of the data given the parameters. So given that we have two Gaussian distributions here, we can do this integral in closed form here and end up with a normal distribution for our data where the mean is still linear in these covariates, but our covariance is now the additive covariance from the error and latent process there. So that gives us this covariance function that has the covariance of the latent process plus the error covariance on the diagonal. Again, in a Bayesian setting, if we define a prior distribution for our parameters, which I'm not going to spend a lot of time talking about here, but generally speaking, these will be non-informative priors. So just whatever that distribution happens to be, again, the posterior inference for our parameters depends on this, on the usual posterior distribution, which is proportional to the likelihood times the prior. Last reason Gaussian processes are kind of a nice tool for statistical modeling is that prediction is really straightforward. So if we take some new set of locations that we want to get predictions of the underlying process, it's really straightforward to get at the predictive distribution here, distribution of the latent process at our unobserved locations, conditional on the data. This first piece inside the integral is available in closed form, given our Gaussian process assumptions. That's going to be a conditional multivariate normal. And then this other piece here is the posterior. So if we've used Markov chain Monte Carlo methods to estimate or to obtain samples from that posterior, we can get a Monte Carlo estimate of our predictive distribution in sort of the usual way. So a very quick crash course here for Gaussian processes and how and why they're useful, and kind of how to use those in a Bayesian setting. Okay, moving on to some of the more specific pieces of this talk here, talking about non-stationary covariance functions. So let me throw a quick definition at you here for the latent process. We'll say that is second order stationary if these two properties hold. So if the expected value of that process for any location S and any separation vector H is going to be the same, so the expected value is the same everywhere. And furthermore, the covariance between the process at location S and some location S plus H, some separation vector there, actually just depends on the separation vector. So here, this C is the covariance function. So what that means here, again, kind of cut to the chase, is that the expected or the mean behavior of Y is the same wherever we are in our domain. And this is not really a problem. Again, we already saw that I include some fixed effects, regression in the mean, so that's a pretty easy thing to get around. But much more seriously, this means that the spatial dependent structure of the process is the same wherever you are on the spatial domain, which is a very restrictive assumption. I'll show you some examples later where this is very much a bad assumption to make. So this is rarely appropriate in practice. It's often made just sort of for convenience, but we want to be a little bit more flexible here in what we're looking at in this talk. So again, what we want to do is instead to allow this Y process to be a non-stationary spatial process. By that, I simply mean that the covariance within the process at two different locations is not just a function of sort of their separation vector. So this intuitively this allows the dependent structure to change over space. So there's of course a very broad literature out there on non-stationary methods. I think some limitations of those existing methods are as shown here. They can be very difficult to implement even for small data sets. So if you start, these days we're more interested in or often encounter larger and larger data sets. So that can be a problem. They're often highly parameterized, so they can be very difficult to estimate, and the computation can be really tricky. And then there's really no sort of off-the-shelf software for using these existing methods. So these are the kind of things we're going to be addressing here in this talk. So again, like I said, there's quite a diverse literature out there on non-stationary modeling. One approach, which is one that I've used quite a bit, which I think is helpful, is a convolution-based approach to spatial modeling, which is very much a constructive approach to building non-stationary covariance functions. So the main result, sorry, I keep jumping around on my slides here. The main result here is that a stochastic process defined on some Euclidean subset can be defined via a kernel convolution as follows here. So, so here K is a kernel function that satisfies some integrability constraints, and W here is a d-dimensional stochastic process. So this is a really helpful framework. You can kind of stepping back from the Gaussian process stuff for a second, you can define very flexible classes of stochastic processes here by different choices of both the W here and also the kernel function. So you could specify some non-Gaussian stochastic process here and end up with some non-Gaussian model for Y. However, in this case, if we do take W to be Gaussian, either Brownian motion or white noise, then what we get is that Y will also be a Gaussian and here a Gaussian process with a covariance function that is defined in terms of these kernel functions. So yes. So that's why I guess I didn't say, but covariance functions in general are very restricted classes of functions. They have to be non-negative definite functions, which again is there's some general classes of non-negative definite functions out there, but it's kind of very difficult to generate new ones or to just kind of come up with new ones. But in this case, we can get a non-negative definite function by way of these kernel functions. So the kernels really only need to satisfy these two very simple integrability constraints, and then what you get is if you integrate them against each other, you get something that can be shown to be non-negative definite. So again, you can kind of plug and play. This is what I mean by a constructive approach. You can sort of choose kernel functions that have particular properties that you're interested in that will then guarantee that you have a valid covariance function. So that's kind of the point of this approach. Again, to be a bit even more specific, which is what kind of leads to the results for this work, is if I choose my kernel functions K here to be spatially varying, so they change over the spatial domain, and furthermore, if I choose them to be Gaussian density functions, then what's nice about this, so if I plug Gaussian density functions into this guy, this is the typical normal case, so I can evaluate that integral in closed form, and what I end up with is this guy right here. So a little bit different things going on here. Here, these capital sigmas are the covariance matrix of the Gaussian densities for the kernel function. So I'll call these the kernel covariances. So that's what's showing up in here, and this Q here is a quadratic form that's specified in terms of those kernel covariance matrices. So this is what you get if you just evaluate that integral in closed form. There's some problems here in that what you kind of have at the core of this is a Gaussian correlation function, which sort of doesn't have very flexible smoothness properties. So there's some work that has derived a generalization of this covariance function that gives you something that's much more flexible. So that's what's down here. I think I'm going to say a little bit more about that here. So this is this is a closed form covariance function, which has been derived as the generalization of that result I just showed. And what's useful here is that the core of the covariance function here is this Matern correlation function, which is a very popular parametric correlation function that is very, very flexible. You can have realizations that are not differentiable at all to realizations that are infinitely differentiable. So that's nice. What's inside here is this Q metric. So this is again this quadratic form that is specified in terms of the capital sigma matrices here. And we have this kind of funky normalizing constant out here because this distance here, well, it's not actually a distance. It violates the triangle inequality. So we need this kind of funky looking thing out here to make sure that we maintain positive definiteness. And then these lowercase sigma terms are kind of marginal variances that we can tackle here to make this a covariance instead of a correlation. So this is a very popular covariance function in the literature, and it's also extremely flexible in the sense that all aspects of the spatial covariance can change over space. So the marginal standard deviation of the process, lowercase sigma, can change over space. And also these capital sigma matrices can change over space as well. So now you can think about these guys. These are the anisotropy matrices. So they allow the range and the direction of the spatial dependence to be flexible. So in some parts of their spatial domain, maybe you could have very short ranges of spatial dependence, and in another part you could have very, very long that might have different directional components. And then if we go back to the error covariance, the tau or the nugget variance, we can also let that guy change over space. So the useful thing here is that this is extremely flexible. The problem is that you have to somehow implement this thing with the data set, right? So we have to parameterize these guys somehow in order to actually use these things. So the approach that we're going to take here, so again, we have these three components here that we have to specify a statistical model for. First, the standard deviation processes, the tau and the lowercase sigma, you can kind of think of a variety of ways of allowing these guys to change over space. So in sort of the trivial case, we could have them constant. That's not really what we want to do, but we'll include that for completeness. We could use a log linear regression, and this is a lot of the things that I did in my thesis were related to the idea of using spatial covariates to describe variability in these covariance parameters. So you could use on the log scale, you could use spatial covariates to describe variability in those guys. You can also apply a Gaussian process to these guys as well. So remember, these are now, you can kind of think of them as themselves spatial processes that are changing over space. So we can use this very low rank approximation where we define a set of knot locations and kind of apply a very smooth or low rank approximation to allow these things to change over space sort of again non-parametrically. So that's pretty straightforward. A variety of choices here. These are just scalar processes, so that's okay. The anisotropy process is a little bit more difficult in that this is a positive definite matrix process. So it's a little bit trickier to specify sort of a modeling framework for this, but we have some options here. So we can use the idea of covariance regression. So this is a regression framework that is valid for positive definite matrices. We can also do some sort of a component-wise regression where we decompose this positive definite matrix into its some sort of an eigen decomposition here. So here gamma is a would be like the principal components, and lambda would be a diagonal matrix of the eigenvalues. So if we're in a two-dimensional domain, like I'll be talking about later, we can allow each of the unique components here to change using some sort of a regression framework similar to as before. Or we can be even more flexible and allow these guys to themselves be Gaussian processes and kind of allow them to vary smoothly over the spatial domain. So again, kind of just putting out a general framework. When you're actually analyzing a particular data set, you'll make some specific choices here, and I'll show a little bit more about that later in the talk. But just as kind of a summary, this is a new framework for modeling non-stationarity in the sense that it kind of brings some new components together, some pre-existing components together in a new way. So we have a closed form covariance function, which is nice because we now don't have to do any numerical approximations in here. It's extremely flexible. There's a lot of different ways to allow the covariance parameters to vary over space, both deterministically via covariates or also stochastically. Particularly for the regression-based functions, we have a very parsimonious representation, which helps us out with the computation, the MCMC. And then another reason that I'll argue that this is helpful is that, especially again when you use covariates, it helps you understand. It provides summaries of why your spatial process is non-stationary. So I think that's the idea of non-stationary modeling is very useful and important, but sometimes it's difficult to infer the specific ways in which your process is non-stationary. So this framework gives us a handle on that. And again, I'll show some examples of this later. Okay, one more quick piece before we get into some examples. So as I know a number of you, there's a lot of great research happening at Texas A&M about this type of thing, but one of the limitations of applying Gaussian processes to modern data sets, and by modern I just mean big data sets, is that when you're evaluating the multivariate Gaussian likelihood, if you have n data points, or here n spatial locations, there's some computational problems. So you have the memory that your computer needs to have is on the order of n squared, where n is the number of locations, and the time it takes to compute that multivariate normal density is on the order of n cubed. So again, as you think about n getting up to several thousand, or nowadays we have data sets with millions of measurements, this is really a barrier that we don't have the computational tools to be able to do this once, much less many times in an MCMC algorithm. And yeah, this becomes particularly problematic when we're doing non-stationary Gaussian processes, just in the sense that you have to evaluate the likelihood many more times because you have more parameters that you're trying to estimate. And again, similar problems if you're trying to do prediction for a large number of locations. So yeah, like I said, including a number of people on this call, there's a large literature out there on ways to get around this. So far, what I've seen, none of these use non-stationary covariance functions. So that's sort of the novel aspect, another novel aspect of this work. And the approach that we're going to use here is a very quick overview of this, is based on the Vecchia approximation. So this is not a new idea, but it has recently kind of experienced a resurgence in this world. So the result here is based on this idea that any joint distribution can be written as a product of conditional distributions. Kind of going back to some of your stat theory courses. So if I have the distribution of, again, YO here is the latent process at the set of measurement locations. So I can decompose this into a product of conditional distributions where the conditional part of this distribution is all previous indices from 1 up to the I-1 location. Of course, there's no computational savings here yet, because as I gets closer and closer to n, we still have very large conditional densities that we have to estimate or calculate. The idea, so this should be 1988, sorry about that. The Vecchia approximation is an approximation in the sense that it replaces these h of I, so these conditioning vectors, with subvectors, where we take some subset of that, and then that gives us this approximation. So again, instead of conditioning on the full set of indices, preceding indices, we condition only on a subset of them. This approximation, of course, converges to the truth as our conditioning sets get larger. But the idea here for computational savings is to keep these conditioning vectors small, so that we're only conditioning on 10, 20, maybe 30 locations. So we're kind of really truncating that conditioning set as we get to larger and larger larger and larger indices. Again, this is a very general framework that, you know, a lot of the methods that are out there can be seen as specific cases of this. Two methods that I'm going to be talking about here, and that have been implemented in the software package, are the nearest neighbor Gaussian process for the response. So this is NNGP-R, and then also some work that Matthias here, and I'm sure some others on the call, have done work with the sparse general vecchia. Both of these can be framed as extending that framework on the previous slide to the joint distribution of the latent process and the data, where the product here is now, you know, we have, again, remember the statistical model said that conditional on the data, conditional on the latent process, the data are independent. So we have an independence piece here for the data, and then we have a piece here that really uses this conditioning set idea for the latent process. And not to get too deep into the weeds here, but what you have to do here is determine a conditioning set for the latent process for each of the latent process values. And the nearest neighbor Gaussian process and the sparse general vecchia specify different algorithms for determining what that conditioning set is. So I don't want to spend too much time on this, but these two methods, and actually many others, can be seen as a special case of this vecchia approximation. And that's something we're going to use to get around these computational limitations. So the point here is, sort of the benefit is that if you use either of these approximations, the approximate likelihood can now be, the approximate multivariate normal likelihood can be computed in linear time. So that gives us much better scaling as we get to larger and larger data sets. There are some differences between these two approaches. Essentially, you can see them as kind of a trade-off between accuracy of the approximation versus speed of calculating the approximation. So the SGV is a more accurate approximation, but the NNGP can be faster. So depending on what your data set or what your application requires, you might want to choose one or the other of these. So yeah, that's just a very quick crash course on approximate Gaussian process methods, and the two that I'll be using in the software package here. So before I get it to an application, I want to just give a brief overview of a little software package for R that I've put together. So this is the Bayes NSGP package. So Bayes NSGP stands for Bayesian Nonstationary Gaussian Process. The point here, again, like I said earlier, is to provide some off-the-shelf software that allows you to implement these non-stationary methods in a Bayesian setting for spatial data sets, and implement sort of everything that I've talked about so far. So from being able to specify the covariance parameters sort of in a variety of ways, to using both the exact Gaussian process likelihood as well as these two approximate methods. The usual problem with this kind of thing is the Markov chain Monte Carlo. So that's another important part of this package. I don't know if anyone on the call is familiar with this Nimble package. It's kind of like, I guess, what were some of the early ones? The Bugs or JAGs were some of the original sort of MCMC tools. And Nimble is essentially a much fancier version of those that allow you to do the MCMC much more flexibly. So that's kind of at the core of the MCMC. You can really specify and adjust your MCMC algorithm to be best for whatever application you might be looking at. It is available on CRAN right now, so you can get it there in the usual way. Again, I don't want to give this is not a software tutorial, so I'm gonna skip specific details, but just at a very high level, there are two outward-facing user interface functions: this NSGP model and NSGP predict, which respectively set up and run your MC algorithm for a generic non-stationary Gaussian process model, and then also do predictions. Again, there's a few required things you have to specify here, like the coordinates and your data. You can also say which of the likelihoods you would like, whether you want the exact Gaussian process or one of these approximate methods. And then for the different covariance parameters, the nugget variance, the process variance, and the anisotropy, you can specify whatever submodels you'd like to use there. So if you want to use one of these regression frameworks, you can do that, or any of the other things that we've talked about. And then the NSGP predict, like I said, takes the output of that MC and does the posterior prediction like I showed before. Just to give you, again, very, very quick overview of the general workflow here is that you use this NSGP model function to create a nimble model object, which is sort of an abstraction for sort of everything under the hood that specifies a statistical model. Then you use nimble tools to set up and run your MC algorithm. So you can customize these samplers here. You can use adaptive sampling. You can do multivariate or block sampling, slice sampling. There's a number of built-in tools that can be used there. The other nice thing about Nimble is that it's fully operated. Everything is done within R, but it has sort of under the hood C++ compilers. So once you've set everything up, you build the MC, build it in the Nimble sense, and then Nimble for you compiles it in C++, compiles the model, and then also compiles the MC. So it's a little bit of a faster execution there than just doing everything in R. But again, this is all done from within R. So I'm not a C++ user, but that doesn't matter. I can still use these. I can still use these things. And then you can run your MC for however many iterations you would like to run it. I do have a few demonstrations or vignettes for this thing. I was realizing as I was putting this talk together, I don't have them up on the web yet. So that's something I need to do. But I'd be happy to share them if this is something you'd be interested in playing around with. We did just publish a paper on this in the Journal of Statistical Computation and Simulation. So there's an open access publication there you can check out, or it's also up on arXiv. So if there's anything you'd like to, any materials I can provide, if you want to play around with some of this stuff, I'd be more than happy to share. This is all free and open. Okay, so that's that. I think we're ready to move into an application of this stuff. Right. So the first one I'll have to share here involves a data set of precipitation measurements over the continental United States. So what I have up here in the upper left panel is the locations and the values of these measurements. So this is these are measurements of precipitation rates. So this is a millimeters per day, how much rainfall falls at each of these locations over over the 2018 water year. So water managers often think of a water year as going from October to September to account for the sort of wet, dry season that we have out west here. We have about 2,300 stations here, where that's again what's shown here. So this is, I've been talking about big data sets. This is certainly not big data in the sense that many of you on the call are thinking about big data, but for non-stationary spatial modeling, this can be actually kind of what we would consider a large or moderately large data set anyway. So the continental U.S. is a very heterogeneous domain, by which I mean it has a lot of different things happening when we're thinking about a process like precipitation. So here in the upper right, I have a map of the elevations. So the eastern U.S. tends to be pretty flat, minus the Appalachian Mountains here in Virginia and North Carolina. But once you get out west, you have really big mountain ranges with the Rockies, also the Sierra Nevada out here in California, and Cascades up in the northwest. So that can lead to very, very different properties of precipitation data, whether you're in the mountains or whether you're out in a really flat, wide open area. There's also a very diverse set of atmospheric phenomena, climate phenomena that produce precipitation. So on the West Coast, we tend to get a lot of our rain from these things called atmospheric rivers, which are these long bands of moisture that come off of the tropics and dump a lot of rain on the West Coast. You guys in Texas are very familiar with tropical cyclones or hurricanes that can produce a lot of rainfall. Up in the Midwest, there's a lot of mesoscale convective systems or thunderstorms. So there's a lot of different processes that lead to precipitation. That's what I mean by it being a heterogeneous domain. So in that sense, it's very important to fit a non-stationary model to these data so that we can really flexibly capture all of these important aspects. So that's my pitch for non-stationary modeling in this case.
Could I ask a question?
Certainly, yeah.
So are you fitting the daily data? So you have maybe 150 days, or are you just fitting the mean data over the 150 days?
Great question. Yeah, so I'm actually just fitting the mean, the annual mean. So yeah, this is the space only. I've sort of averaged over time just to get to sort of what the you know, I could have, I guess, just as well done the total precipitation over the year. So this is kind of the mean precip instead of the total precipitation. And that is a good point. I do have this plotted on the log scale. So I'm going to also be modeling it on the log scale so that the Gaussian process assumption is a little bit more appropriate. But yeah, thanks for the question. Okay, so to kind of, you know, use the framework that we've been talking about here, check time. So we have, you know, we have our generic non-stationary framework here. We can now think about sort of how we actually want to apply that in this case for this application. So we have I'm going to use a spatially constant mean. This might not be the best assumption, but in order to kind of to focus on the second order properties of the data, we're going to keep the mean the same everywhere. And furthermore, we're going to keep the nugget variance to be the same. So that's the, think about that as the measurement error. So we're using, you know, we have a sort of a single network of weather stations. So that's kind of why we think that maybe a constant error variance over CONUS is okay. In terms of the spatial variance, we'll let this vary smoothly over the domain. So we're going to use that approximate Gaussian process, the low rank stationary Gaussian process model to this using a fairly coarse grid of knot locations. And then as far as the anisotropy, which is that capital sigma process that I was talking about earlier, as I was sort of suggesting, the magnitude, so the sort of the length scale of the spatial dependence and also maybe directionality is definitely going to depend on elevation, particularly in the Rockies and on the West Coast. But the way that which elevation interacts with precipitation could also change over the domain, whether we're talking about the East Coast and the Appalachians versus the Rockies versus the Cascades. So I'm going to use this this component-wise regression framework here, where I let the components of that anisotropy change linearly with elevation, but then also have a longitude interaction there, so that I can capture different I can capture different relationships between elevation and the dependence of precipitation over the domain. Like I said, this is not a very large data set in the grand scheme, but in this case, this is kind of a large data set to deal with. So I'm going to use the SGV likelihood approximation to speed up the calculations of the computation here a bit. So to say a little bit more about the MCMC, I do have a moderately large number of parameters to sample here, 67 total. Most of these are coming from that the spatial variance, where I have to estimate the latent stationary Gaussian process parameters here. So that's giving me quite a few parameters to estimate. I mean, I have plenty of data, so that's not really a problem, but getting my MCMC to run here can definitely be a challenge. So I'm going to use, for most of these, there's kind of straightforward ways of doing this. I'm just going to use univariate random walk samplers for the mean and nugget variance and hyperparameters here. I'm going to use a block sampler for the anisotropy components. So those regression coefficients for the anisotropy terms, I'm going to sample those sort of in obvious ways, in obvious blocks sort of within each component. I do need to get a little bit creative for the latent process values, in that we have, again, 50 parameters that we need to estimate that are all very highly correlated. So, but we probably can't apply just a single block sampler to all of those. That's probably not going to efficiently sample from these parameters. On the other hand, using a bunch of univariate samplers is not going to mix very well, given that we likely have this high posterior correlation. So instead, I'm going to, again, using this software package is nice because I can very quickly try out a bunch of different sampling schemes. So the pluses here represent those knot locations. And I'm going to do a couple different things where I try a couple different things where I first apply a large block sampler to all 50 of these guys. And then these scheme 2 and 3 where I do 5 sort of large blocks. So I have anywhere from 9 to 12 spatial chunks here that I'm going to sample, or maybe you can go even smaller and use only 3 to 4 in each one of those. So I'm going to block the sampling of these guys according to what the color you can see there. In order to sort of evaluate which one of these is best, we can use the efficiency. So here the efficiency is the effective sample size, or the number of independent samples effective number of independent samples you have from your MCMC divided by the compute time. And so what I'm showing here is the efficiency across the different parameters. And the box plots here are the fact that we have more than one. We have a set of parameters for the anisotropy and the spatial variance. So kind of looking across these guys, the different sampling schemes perform better or worse depending on which parameters I'm looking at. But overall, the second scheme seems to maximize the efficiency kind of across the board here. So that's the one we'll go ahead and use sort of for the final results here. Like I said, a nice benefit here is that of these type of non-stationary methods is that you can get nice summaries of why your data exhibit non-stationarities. So look at a couple summaries here. In terms of the anisotropy, remember we use this regression framework, so I have a set of regression coefficients. In terms of the eigenvalues, so this gets at the sort of the length scale of the process. The coefficient posterior mean and credible intervals are shown here. And we can see that there's a significant effect of elevation in both the first eigenvalue is the east-west dependence, and the second is the north-south. So in both directions, you can see that there's a significant effect of elevation. And these guys, the elevation coefficients are negative, which means that when you get to higher elevations, you have shorter ranges of spatial dependence. So that is very much consistent with what we would expect. This interaction coefficient is significantly different from 0 in the x direction, which again tells us that the relationship between elevation does change significantly as we move from east to west across our domain. To make this a little bit more visual, a different way of plotting the same results here is this is the posterior mean of the average anisotropy range, so the average eigenvalue here. And so the units here are a distance. So you can generally see that there's much longer ranges of dependence along the coast and much shorter ranges of dependence when we get up into the mountains, which again is very much what we would expect. To look at the spatial variance, so this is the posterior mean surface for what the spatial standard deviation looks like. Again, the units here are now the same as our data, so log millimeters per day. And you can see that there's much more variability, say, in Southern California than there is over much of the eastern part of the United States. So again, I think that's very much what we would expect. And if you look back at the data, you can see that there is much more variability in the eastern part, in the western part of the domain. Last piece is the posterior prediction. So again, using this framework to get at both prediction. So our data are sparsely observed. We want to kind of get a better picture of the spatial distribution. We can look at these prediction maps. So again, here I have the posterior mean and the posterior standard deviation. Clearly, in the standard deviation over here, as usual with the Gaussian process, you can sort of see where the measurement locations are, that our uncertainty decreases as you get close to a measurement location, which makes sense. But you can also see that the non-stationarity gives us sort of, aside from that, gives us very different uncertainty across the domain. So we have a lot more uncertainty in our measurements out west as opposed to in the eastern US. So kind of a nice final benefit of this non-stationary method is it gives you a better sense of your spatial, of the uncertainty over your spatial domain. So I did have another example, but I think I'm going to skip over that out of time. But just to point out that I did apply these methods to a data set with more like 50,000 locations that was still doable on a laptop. So last piece, just in closing, just wanted to show some compute times that use the software that I've been talking about to evaluate Gaussian likelihoods for the different likelihoods and their approximate methods. So yeah, like I said, nowadays a lot what we mean by big data sets in the spatial world is when we're getting up to several million measurements, and that's you know, these same methods can be applied there, but what you often need is some sort of a custom computing environment where you're maybe using a high performance computing to split up the likelihood calculations across different compute nodes. So this software is not going to work for that. This is all being done on a personal laptop. So this is not something that's scalable to millions of measurements, but it's definitely scalable to tens of thousands of measurements. And again, kind of the nice thing here is that you don't need a fancy computing environment. You can do all this on the laptop. That even if for the NSGP at least, even if you get out to 10,000 measurements, you're only a little over a second, maybe 2 seconds to evaluate that likelihood, which is good enough, I guess, for doing something on your laptop. So that's it. I'll end here. Like I said, there's a paper draft up there on arXiv if you want to check that out. I'd be happy to share any sort of vignette type tools offline over email if you're interested. So shoot me an email if that's of interest. But thank you very much. That's the end of the talk.
All right. Thank you very much, Dr. Risser. It was a very nice talk. So
Thank
it's
you.
time for questions. Do we have any questions from the audience?
Can I ask one question, quick one?
Sure.
Yeah, of course.
Okay, Mark, fantastic talk. Like, it cleans up so many things and it clears up.
Oh,
Just
thank
as
you.
a comment of this non-stationary processes, this is one of the ways of modeling when you put this big covariance structure and you model it. There is an alternative way, what we started long time back, is local modeling. So
Right.
you look at a non-stationary process as a local stationary processes, like piecewise Gaussian kind of thing, and then you try to mix over that and capture any non-stationary process. Okay, so and this big data period, it's very essential because the patch of stationary processes possibly can put in a parallel computing and do them parallelly, and because they are piecewise, and then do the model mixing at one stage and see how you predict. I love to see some of this big data. I know we have an outstanding colleague, Huiyan Sang, she picked up that method, and Huiyan is doing some outstanding job. Not with tessellation, but she's doing some tree structured partitioning, very cool kind of thing, and working very well in pretty moderate size of data. I love to see some of these comparisons in future, possibly to see how this global model versus local model works, because one good property of this local model is here you can do some maths. You can show that piecewise non-stationary process always approximate a non-stationary process, and how fast also you can see. I know in big data that's not a concern. You have so much data, always so rate of, but at the end of the day, possibly that will be a competitor in future to see how these two methods work, and possibly they'll give you the same results or something like that. Just a comment.
Oh no, that's fantastic, and I do think that the sort of local, well, there's a lot of good reasons about what you just said. I mean, it allows you to sort of more flexibly model the non-stationarity, maybe in the sense, you let the data speak for itself. I don't have to pick, like a regression model or something like that to specify how the correlation range is changing. It's helpful for computation that you can split everything up and do things in parallel. That's absolutely right.